What we are going to do. Okay, so the proof continues here. So to show 2, we show M divides A. So if we can show M divides A, then using symmetric arguments, we can get M divides B. So we will have M is a common divisor of A and B, and this implies M has to be less than or equal to GCD of A and B. So this is our strategy. So we are going to show M divides A. We have not shown this yet. So we are going to show this here. But if we can show M divides A, then A and B, they are actually equal thing, right? So if we can show M divides A, then we must be able to show M divides B. And after that, we now know if we can show M divides A, M divides B, then M will be a common divisor. A common divisor must be smaller than the greatest common divisor. Does that make sense? Yeah. Any student in this class must be shorter than the tallest person in this class, right? So that's why that person is called the tallest person. So similar here. So if M turns out to be a divisor, a common divisor of AB, then it must be smaller than or equal to the greatest common divisor, because we call that greatest common divisor, so it must be greatest. Okay, so this is the idea. So all it remains is we want to show M divides A, so we don't know. So this is what we are going to show. Okay, so we are going to show here. So it remains to show M divides A. So how can we show M divides A? So let's take a look of what happens when A divided by M. What is going to be the quotient and what is going to be the remainder? If we can show that the remainder is 0, then M divides A. So this is the idea. Okay, so let's take a look. Okay, so division theorem says A can be written as some quotient times M plus some remainder when it is divided by M with R between 0 and M minus 1. Is that okay? So far so good, right? So far so good. So this implies what? So first, but then let us recall, what is M? M is some linear combination of A and B. So we can write this as A can be written as Q times SA plus TB plus R. Is that okay? So we keep the same R. Is that okay? And then we will have R. R is equal to, so we arrange the term. So R will be equal to Q times SA plus TB minus A. Is that okay? Is that okay? Recall, what is R? R is in between 0 and n minus 1. Okay. Now, so far, it doesn't make any sense of what we are doing. But then, we are claiming that R has to be equal to 0. It has to be equal to 0. If R is not 0, then so what is R? R is something like this, right? R is a linear combination of A and B. And M is the smallest positive linear combination of A and B. If R is not 0, let's say R is equal to 2, it's not 0. Then in that case, we find a smaller positive integer, smaller than M. And then it is going to be a linear combination of A and B. This is not okay. This contradicts with the choice of M. M is already chosen to be the smallest positive integer. That is a linear combination of A and B. So we cannot choose any other number for R. R can only be 0. If R is non-zero, then R is going to be less than M. Okay, because R is less than M, right? If R is some number less than M, but not 0, then it contradicts with the choice of M. So that means that R has to be equal to 0. Is that okay? Good. What does that mean? So if R is equal to 0, then this overall thing actually means that A is equal to QM, because R is not 0. So this implies M is divided by A. And then we are so happy. So this is now done. Okay? That's it. Okay? So look at this. This proof gives a really non-trivial result. So physically, the GCD is the common divisor of two things. But then, based on this new theorem, we will have a new interpretation of GCD. It is the smallest positive linear combination of A and B. And it doesn't look that trivial from what we read it. Okay? So I hope you like it. Okay, I've overrun for the first class, so let's take a 15-minute break. And then please come back at 3:30, and then we will continue. So let's resume the class. Okay. Now we are going to look at a few more. So we have 1, 2, 3, 4 already. So we are going to look at a few more simple results. So although these results are simple, that you will believe that they are true, but then the proofs are not that trivial. So let's try to work it out. So I've copied the current result that we have about GCD here. So first of all, this is the definition. GCD is the largest common divisor that it can divide A and B properly. But then from the theorem that we have just shown, it is also the smallest positive linear combination. So it is also a linear combination of A and B. Okay, so these two are very useful. So we will use them to represent GCD here. So first of all, the first one, so we will find out that every common divisor of AB will also divide this GCD of AB. So let's take a look of some examples. So for instance, let's have two numbers. Let's say we have 18, and then we have 30. Is that okay? So what is the GCD of these two? So it would be 6. Am I correct? So 6 is the GCD of them is equal to 6, right? Okay. Now, what are the common divisors of them? So is there any other number that can divide both of these two numbers? So first of all, 1 is a common divisor, right? 2 is also a common divisor. 3 is also a common divisor. And then 6 is a common divisor. It turns out that 6 is the largest one, so we call it GCD. And then each of these common divisor also divides the GCD of the two numbers. So this is the property that we know. Okay. So when we are in the primary school, we have learned the unique prime factorization of a number, then we use that to find out the GCD of two numbers, and then so this is usually quite obvious for us that it is true. But now we don't have this unique prime factorization result yet. So how can we still show that every common divisor of A and B also divides GCD of A and B? It's just two observations. One is, what is GCD? So GCD is a linear combination of A and B. And then common divisor divides A, and common divisor divides B. So a common divisor divides any linear combination of A and B. That's it. Is that okay? Okay, that's it. So here we are actually combining what? 3 from above, and also the theorem that we have just shown. Linear combination result. Okay, that's it. How about this one, the next one? GCD of Ka, Kb is always equal to K times the GCD of A and B. So we can actually pull K out. If K appears here, if K appears here, we can take K out. So why is it true? Okay, one direction is easy. Okay. So here, to prove this, we want to show what? We want to show that GCD of Ka, Kb divides K times GCD of AB. We also want to show the vice versa. K times GCD of AB will divide GCD of Ka, Kb. So we want to show these two things. Because each of these numbers are positive. GCD is the largest number, so it's greater than 0. Assume we are not talking about 0 and 0 for A and B. So if one divides the other and the other also divides back the first one, then these two numbers has to be the same. Okay? So this direction is easy. This direction is, it is because of what? Because okay, so because GCD of AB is a linear combination of A and B, right? So it's a linear combination of A and B. So it is equal to SA plus DB for some S and T. So if we multiply K to it, then we will have this one is equal to K times SA plus TB, right? So this is equal to what? S times Ka plus T times Kb. So it means what? It means GCD of Ka, Kb divides this number. Is that okay? Does that make sense? Because GCD of Ka, Kb divides this part, GCD of Ka, Kb divides this part, so it divides the linear combination of them, so it divides this one. Okay? Okay, the other side. Let's try. Okay. Okay, the other side is similar. So GCD, so what is GCD of Ka and Kb? So it is equal to some linear combination of Ka and Kb. So let's call it equal to U times Ka plus V times Kb for some UV. Is that okay? Is that okay? Any result that we can apply? So first of all, we know what? Ka so we want to show that K times GCD of AB divides KA. We are claiming this is true. We are claiming this is true. The reason is that GCD of AB divides A, right? So this is so there is some number W times GCD of AB is equal to A. Does that make sense? So if this is the case, then KW times GCD of AB is equal to K times A. Does that make sense? Well, we exchange these two, so Ka is equal to W times K times GCD of AB. So Ka is written as K GCD AB times an integer. So in that case, K GCD AB divides Ka. Is that okay? If you're okay with this, could you please raise your hand? Okay, now we have K GCD AB divides Ka. We also have K GCD of AB divides Kb using similar arguments. So it divides this part, it divides this part, so it divides the linear combination of them. Okay, so this implies what? This implies the result. This implies K times GCD of AB times GCD of AB, it divides the GCD of Ka, Kb. Is that okay? That's it. So we get the result. So we get this number divides this number, the product of these two divides this number, so they have to be the same. If you're okay with this, could you please raise your hand? Okay, good. The third one says A and B does not have any common factor. A and C does not have any common factor. So A and the product of this BC will not have any common factor. Well, obvious, right? If you think about each number has a prime factorization, you cannot get any common factor, you cannot get any common factor. So even though you multiply B and C together, you still cannot create a common factor between A and this product. Okay, but here we don't. We don't have this factorization theorem, prime factorization. So how can we prove? Amazingly, the proof is super simple, super simple. So because GCD of AB is equal to 1, then we know what? We know that there exists some S times A plus T times B is equal to 1, right? Similarly, because we know that A and C has no common factor, so there is some U times A plus some V times B, so V times C is going to be equal to 1. Am I correct? Okay, multiply these two together. So we will have SA plus TB times UA plus VC is equal to 1. Am I correct? Okay. So this one, we can expand it. But each term, either you will have an A inside or you will have BC inside. Is that okay? So let's expand it. So we will have what? We will have S times U times A squared plus S times A times V times C, right? So we just expand it, plus T times B times U times A plus T times B times V times C is equal to 1, right? So this one gives us this one. But then we will rearrange them so that this is going to look something more suitable for our proof. So we will get something like A times SUA plus SVC plus TBU plus BC times TV is equal to 1. Is that okay? Well, so complicated, yeah. But then we find that 1 is a linear combination of A and BC. So GCD of A and BC has to be 1, because 1 is the smallest positive integer. And then it turns out that 1 is a linear combination of A and BC. So 1 has to be the greatest common divisor of A and BC. Okay? Does that make sense? Okay? Good. So we get 3. How about 4? How about 4? 4 is if A divides BC, but then AB doesn't have any common factor, then we will know that A has to divide C. So how do we prove? So